Okay, so let's get going here. Lecture number 5 is due Thursday, November 8th. Test number 2 officially will be Thursday, November 15th. I actually finished writing the tests yesterday. Are there any questions?
On the project, there are several questions that just say kind of do this, where it would be, do it in R and get the output and whatever, without any kind of explain type part to it. Do you want us to explain, answer, like when one of it says, do the permutation test? Do you want an interpretation of the test at the end? Or do you
yeah, I mean, it would be nice if I know if you reject or not.
Okay,
yeah,
okay.
Yes. Any other questions? Okay, we left off then in the notes on page 418. So we're going to go back and do permutation tests. Hopefully finish the chapter today. So just to help you remember where we're at in terms of the big picture, before coming into this class, if you were to do a hypothesis test, you'd come up with some kind of distribution for y under the null hypothesis, and you'd calculate a particular test statistic, let's call it t, and you'd be interested in what's the probability of t being that extreme on the distribution, and that will give you your p-value. Now with the Bootstrap test, essentially what we do is we replace this continuous nice density function with a histogram, and we're going to basically do the same thing with a permutation test so that we can get some kind of measure of how extreme is our test statistic relative to what we would expect it to be under the null hypothesis. So with these permutation tests, and I think I mentioned this before, they're actually quite old. They predate the Bootstrap. Bootstrap, generally speaking, was invented about, or at least Efron's first paper on it was like 77, 79, 79 around there. The permutation tests were around a lot longer than that, and I actually took a readings class with a professor at Kansas State when I was a student there. We were reading papers from the 1920s and 1930s about how people would do these permutation tests. The problem was they didn't have the computing power to really do it, so they had to resort to various approximations. So a permutation test is actually just a special case. You can think of it as a special case of the Bootstrap, okay? Just in general sense. The main difference is this. With the implementation of my red pen, red pen. Okay. With the permutation test, it's actually based upon what's called conditional influence. And you probably touched on that maybe a little bit in 883. Generally speaking, we'll always touch on this in in an advanced inference course, or 983, 982, where our p-value that we're eventually going to calculate, it's a probability, and it's conditional on a sufficient statistic. But the sufficient statistic is such that it's a sufficient statistic under the null hypothesis distribution. So let's say F0. Okay? Now, from your 883 days, you know that order statistics are sufficient statistics. And one way to think about this is that we're actually going to be conditioning on these order statistics, but not necessarily the order statistics that you would exactly expect. Let's see what I mean coming up. I'll give you an example. Also with this permutation test, we end up resampling, just like what we did before, but the resampling is done without replacement. I might be thinking, well, wait a second, if you sample without replacement, aren't you going to get the same resample every single time? Yes, but you'll see with how we look at then this resample, you'll see why we actually get a different statistic for every single resample. Okay? So that then this is what our p-value looks like. So probability t star is greater than or equal to t if we only had, let's say, evidence against the null hypothesis with large values. Given your sufficient statistic, let's just call it S. This could be a vector. And the null hypothesis is true. Now the notation maybe can get a little bit messy here because you might be thinking, well, why don't I have f hat 0 there for the conditioning part since I don't have a star right here? Well, by us putting the sufficient statistic in HO, it's kind of assuming, yes, we're taking our samples from f hat 0. We are actually doing that. So that's why you don't see that notation there. Let's take a look at an example. This is a two-sample test for the difference of two means. We already talked about the Bootstrap version of it. If you remember, with the Bootstrap version, there was 4 different ways that we could take a resample. One of those ways is going to be used for permutation tests. There's only one way to do it. Okay? So here's our null hypothesis and alternative hypothesis. You know, generally speaking, you expect that if I took the difference of 2 sample means, that will be a good statistic to use to judge if the population means are the same or different. Okay? So we're going to let t be y bar 1 minus y bar 2. And our data, you can write it out symbolically as you would kind of expect, y11 through y1n1, where the first subscript says, well, which sample is it? N1 is the sample size for population 1, and y21 through y2n2. Okay. We need the null hypothesis distribution. We need f hat 0. Well, in one of the ways that we talked about with respect to Bootstrap, we said, well, how about we just assume that this data comes about through one distribution? If it comes about through one distribution, of course, then each of the sample values then comes from a distribution that has the same mean, because it's the same distribution. So we can say F0 actually, let's say, generated or this data came about through this F0. So now we have a way to say that, yes, this is our null hypothesis distribution. So then what that means then is if we're coming from the same distribution, we have the same mean, you know, whatever these subscripts are here, you could say are just coming about through chance, because they're coming from the same distribution. Okay? So what we're going to do then is then take our f hat 0 to be EDF of our sample. That's it. Now, how do we resample? As I said before, we're going to actually resample without replacing them. So what we're going to do is simply resample N1 of these Y's. So just forget about the subscripts. Think of these as actual numbers. Maybe this is the number 3. Maybe this was observed to be 3.5. Maybe this was 2. Maybe this was 1.5, and so on. We're going to resample N1 of these numbers and say, perhaps this came from population 1. Then the remaining values, there's going to be N2 of them, we're going to say, suppose that came from population number 2. In essence, all we're doing is, you could say, permuting our data. We're just kind of mixing the data up, permuting it, and say, let's say maybe the first N1 are from population 1, the second set of numbers. There's n2 of them. That's for population number 2. That's where the name permutation test comes from. In the end, there are n1 plus n2, choose n1 different permutations that could occur. Obviously, well, let me say this, the exact permutation distribution then of T is found by looking at all those different permutations, calculate T, well, maybe we call it T star since now this is actual, and actual it's a resample, and there's your distribution. So just like what we saw in our project number 1 in chapter 2 as well, you could actually iterate out every single possibility and calculate the actual true distribution. Of course, though, in most applications, that this n1 plus n2 choose n1 is going to be large. So what we can do is randomly generate, let's say, capital R, these permutations, and use that to help us calculate a p-value. So, for example, for the hypotheses that we were looking at, here's a two-sided test p-value. Basically the same expression that we've seen before. One could also use this p-value, or this measure, or this formula. Put these on the same screen. When do you think these two p-values will be about the same? Under what conditions would you expect these to be about the same? So notice what we're doing with the first one here. We're taking the absolute value of T star. Is it greater than or equal to the absolute value of T? When the distribution is symmetric. Exactly. Symmetric about 0. That's the key. So if you were to do a permutation test and it was a two-sided test, but it was not symmetric about 0, don't use this one. You can draw it out. You draw a skewed distribution, for example, to see why this would not be appropriate if your distribution is not symmetric about 0. By pointing this, I wanted to just point this out because I mentioned at the beginning of chapter 4, there's more than one way to calculate a two-sided test p-value. I just want to show you that this is one way that's commonly used. Okay. Again, notation. Maybe we should call this p, p star, or maybe p perm. Let's just call it P. So let's take a look at an actual numerical example. This comes from Jim Higgins' non-parametrics book. Well, there's no program for it because we're going to actually calculate the exact distribution. So imagine a situation where you have some test scores from 7 new employees of a company where 2 different methods of, let's say, instruction were used to get them ready to go and work. With the new method, the first person got a score 37, the second person 49, and so on. With the traditional method, that had been used, let's say, before, the first person got a 23. And what we like to know is there a difference in population means here? Why? Well, you want to know, for example, is the new method better than the traditional method? You quantify better in terms of the mean. Okay. So, in this particular case, then, there are 7 choose 4, 35 different possible permutations of the data. Here is one possible permutation. All I did was I flipped these numbers. Now, under the null hypothesis, where we assume that everything's basically coming from the same distribution, every single permutation is equally likely. So this has an equal chance of occurring, as does this, which was the original data. Now note here, if you remember we were conditioning on a sufficient statistic, the order statistics are exactly the same, meaning If I were to order all these values here and order all these values here, it's exactly the same for every single resample. Think about how you would do this with respect to a bootstrap. You would actually resample with replacement. Would the order statistics change? Yes, it could, because you get the same, let's say, same data value more than once in a sample, or maybe not at all. Oops. Okay. So, what's going on? There we go. So here's actually just simply a scanned image from Higgins's book. And he actually wrote out all the different possibilities of what could happen. Here is what actually did. Notice how these are sorted by difference between means. In other words, RT. Or you could say T star. So T star, which is equal to Y bar 1 star minus Y bar 2 star. And you can see that maybe they're not sorted. Excuse me. No. Okay. I guess they're sorted in terms of the numbers. They're sorted in terms of sum. But still, if you look through all these numbers, you can see that the 16.2 is kind of extreme in terms of its distance from 0. Because, of course, at t equals 0, the null hypothesis is, let's say, exactly satisfied. So you can see that the 16.2 is kind of extreme. And again, remember, this is calculated assuming the null hypothesis is true. Whenever you have a statistic that's extreme with respect to a null hypothesis distribution, that should say, maybe what I observe is unlikely. Thus, maybe my p-value will be small. And thus, should reject HO. Well, let's look at what happens here if we were to calculate a p-value. We're going to do a two-sided test first. And the way I'm going to calculate the p-value is through this particular method here. So 1 plus the number of these absolute value t star r's greater than or equal to the absolute value t over r plus 1. Essentially then, what that means is there are 4 values. Here's 2 of them. Here's the other 2 that are greater than 16.2, greater than or equal to 16.2. There are 35 total possible values or resamples, so thus my p-value is 0.1389. So, it's kind of small, but still maybe not small enough to say, oh yeah, maybe there is truly a difference. Well, how about if I calculate the p-value like the way that's shown on page 421? So what that means, I take 2 times the minimum of 1 plus the number of t stars that are greater than or equal to t, 2 of them, divided by 1 plus 35. The minimum of that versus 1 plus the number of t stars that are less than or equal to t, which ends up being just 34 of them. So all you're doing is looking at, extreme in one direction or the other, so that in the end my p-value is 6 over 36. Get that right? I just wrote it down wrong in my notes. 6 divided by 36, which is 0.167. So that's how you calculate the other way. Let's compare this. This is on page now 24. Let's compare this if I were just to do a regular old t-test. course, there's typically two different ways to do a t-test. You can say var.equal true, var.equal being equal to false. And the important thing to look at here is the p-value. Two tests. And they're somewhat similar to what we had. But remember, we didn't have to make any assumptions about, normality, which these t-tests do. Why do you think I looked at var.equal true? Why did I want to use that versus maybe, I guess normally when I teach a set 801 course, I always look at just false.
Is it because when we're doing our permutation test, we're assuming that while the means might be the same under the null hypothesis, the variance?
Exactly. Because you're assuming the same distribution.
Right.
Well, that's why. So obviously there are assumptions with the permutation test, but not necessarily as extreme as with the regular t-test. Well, how about a one-sided test? This might be more of interest in this particular problem. The subscript 1 corresponds to the new method. The subscript 2 corresponds to the traditional method. And typically in a setting like this, you would like to see if there's evidence that the new method has a higher mean than the traditional method. So that's why I constructed my hypotheses like this, where I have a greater than in the alternative. So in this particular case, you're looking at, well, how many of the T stars are greater than what was observed? There was 2. So the p-value is 0.0833. If you were to do the regular old t-test, this is on page 425, you get a p-value of 0.04578 for different variances and 0.06 for equal variances. So, it's quite interesting. I mean, this is, really a simple idea. And look at how you get just about the same answer with less assumptions than you would with a regular old t-test. Okay, so page 425. So we already talked about the second bullet here. That's the about the sufficient statistics. Something else that you could do too that's interesting, and you could do this with the Bootstrap too, although we haven't focused on this, and that is you could use more robust versions of the test statistic. So for example, use a difference medians or trim means. Now obviously that changes your hypotheses some, but perhaps if you're looking for central location, difference of central locations, that would be of interest to do something like this. So, instead of just taking y bar 1 minus y bar 2, why don't you take some, trim mean from sample 1 minus trim mean from sample 2. Obviously, we want larger sample sizes than what we had for our particular example, but that's what one could do. Also, what one could do is, how about replace the data with their ranks? What do I mean by that? Let's go back to our observed data again. So we can see that the smallest data value is 23. So why don't you replace that with a 1? The next smallest value is 31. Replace that with a 2, and so on. These are my ranks. And basically do a test for the difference in mean ranks. Perhaps some of you have heard about that kind of test before. That's the Wilcoxon rank sum test. Often in a non-parametrics class, you learn about some normal approximation to it. Well, there's no need to do that because you can just simply do a permutation test version. So page 426 then, as I stated here, when I alluded to when we were first talking about the Bootstrap version of this test, the possible problem here is that we're assuming that we have the same distributions essentially in the null hypothesis. Which may or may not be true. It might be reasonable that, if you think in terms of this this test situation that we have from our example, that all that's going to happen with this new test is just going to simply shift the distribution maybe up, but still keep the same shape to the distribution. That's a reasonable assumption. So in actuality, what you can say is that we're doing this in our test. Suppose F1 is denoted some F1 is the CDF form for population 1. It's denoted by H of Y. In F2, the CDF for population 2 is denoted by H of Y minus delta. So there you see that delta shift. And what we're actually testing formally is this. Is delta equals 0 versus delta does not equal 0. So because of this, some people don't like this approach, don't like the permutation approach because of this extra assumption. But I don't know. I guess I still think it's reasonable. It's an intuitive way to approach a problem, and I like it. Here's a question then for you. Suppose you have one sample from a single population. With this sample, you would like to test, is mu equal to mu 0 versus mu does not equal 0. How could you do this with a permutation test? Think about what your resamples would look like. Perhaps this is a trick question.
So your hypotheses make sense. Mu equals mu 0 and mu 0 equals 0.
Thank you. Well, that made it even more difficult for you.
I was looking at that like, okay.
Well, actually, this is, I guess, even a bigger trick question than I had originally intended because you can't do this with the permutation test. This is one of the problems with, I guess, another problem with permutation tests is that you can't do simple things like this. Because the problem is that what a resample would be is that you can't really arrange it in a way that you want to get the exact same data for every single resample. So remember, we need to condition on these sufficient statistics. So, you can't do it. Let's look at how we can do a permutation test for the Larry Bird data set for testing for independence. So we already looked at this in terms of a bootstrap test. Now we're going to look at it in terms of a permutation test. So just as a review, we have results from Larry Bird's first free throw attempt, results from Larry Bird's second free throw attempt. We have everything arranged in a nice little contingency table structure. And we want to know, is the second free throw outcome independent of the first free throw outcome? So here's what our hypotheses look like. We can put the data into R using the array function. It allows us to construct a contingency table. What we are very interested in, though, is a different version of the data, which is what I often refer to as the raw data version. And let me go over here to this to construct the raw data version. So it's in all.data, and basically what we have here, all the way to the top, we have a column in this is actually a matrix, which represents the row number. We have a column here representing the column number. So for example, there were 251 individuals that had row 1, column 1. So if I just page down here, eventually, you will see that I have 251 1-1s. And then I'm going to have 34 1-2s, 48 2-1s, and 5 2-2s. So that's my raw data. And if we turn to page 29, we see that how to do this test. You could use the chi-sq.test function, which two different ways to do it. You could use it with the contingency table itself or the raw data, which we will actually use this format coming up. And the Pearson test statistic for independence is 0.2727, PI 0.6. Okay. Well, let's talk about now how we can do the permutation test version of this. In this particular case, you can still think of your sufficient statistics as your your order statistics. That's the summary. In this particular order, I'm sorry, I'm getting ahead of myself. Because it's easier for me to explain this. Remember how we did the Bootstrap test? And that was we randomly sampled from the first column of all data. In other words, randomly sampled from all the row numbers, and we randomly sampled from the column numbers, all with replacement, and we basically put them together to form a new contingency table. We can do almost exactly the same thing here, except for now we're going to resample without replacement. So when I do this in terms of the row numbers, all I'm doing is just shuffling the row numbers. All I'm doing is, well, for the column numbers, I'm just shuffling the column numbers. And since I'm doing this independently of one another, that's how we incorporate the null hypothesis. Let's relate this to what null hypothesis means in terms of this contingency table situation. It basically means that you do not, all you need is information about the rows, the row totals, and the column totals. In fact, the sufficient statistics, you could say, are simply n1 dot, sorry, actually I'm using n1 plus here, n2 plus n plus 2, n plus 1. Meaning that that's all you need in order to find the stuff that's in the middle of the table, in terms of, these are counts, but in terms of probabilities. That's what independence means in your contingency table setting. So what's going to happen then for us is that for every resample that we get with a permutation test, we're going to have exactly the same row totals, exactly the same column totals. And hopefully that makes some intuitive sense why that happens. Because all we're doing is just shuffling the row numbers, we're shuffling the column numbers and putting them back together. You're not changing the number of ones and twos you have. Unlike with the Bootstrap, which could change them. Most likely it would change them. Okay. So here's an outline for how to perform this test. Put the data into a raw format. Excuse me. Permute the row numbers, permute the column numbers independently of each other. Then put these permuted row numbers and column numbers back together into a data frame or matrix. Calculate x squared star, repeat r times, and calculate your p-value. Okay. Now, we can actually do this test slightly more simply. In other words, all we need to do is just permute either the row numbers or either the column numbers, just one of them. Because all we're just basically saying is this: what happens with the column is independent of what happens with the row. So since we're keeping always the same number of numbers of ones and twos, we can simply get away with, how about we just permute only the column numbers? Just a simple thing. And that's what we're going to do. So how can we do this in R? Jump over here to 10. I need a calc.t function. What I'm going to pass into it for my data are the column numbers. I is going to be the indices. That's going to tell me what ordering the column numbers should be. And then also I'm going to pass in the actual observed row numbers in its original form. Perm.data gets, well, my permuted data, permuted column numbers. And then I use the chi_sq.test function as I have done before, where I have the row number here, I have my column numbers here, and then just put out the statistic. So let's actually try this with the observed data. So here are my column numbers. Here are my indices. Here are my row numbers. And I get what was observed. Okay. Here's then the permutation test. Set a scene, number of resamples, probably should have used more. Boot function, data equal, here are my column numbers. My statistic is calc.t, r is equal to 999. And here's basically the new thing here, sim equal permutation. So this tells R, sample without, sample without replacement. And then I pass in also my row numbers. Let's run it. Okay. First of all, what we see here is a histogram. Look at how discrete the histogram is. QQ plot, I also plotted on a chi-square 1 scale. And you can see that the distribution is quite discrete. But if I had to use a chi-square approximation for it, it seems to do the best it could, because it's kind of going through the middle, to some respect, of those numbers. Or let me actually walk over here. Sorry for those people who are watching the video. It's kind of going through the middle of these numbers as we see, or these values. Okay. So what about the p-value then? Let me actually jump back forward. Well, just as we've done before, sum up these t stars. How many are greater than or equal to t itself? I get a 0.629. Again, we had 0.6015. We're using an asymptotic chi-square 1 approximation. So we're getting just about the same results. That's good. What that's telling you is that the chi-square 1 approximation works. Remember, there was a little bit of worry if it would or not, because we had a count of 5 in one of the cells, which was kind of low. Here's page 433. Here's some more information about just how discrete this distribution is. If I use the xtabs function, I can use the table function as well. With the t stars, you can see that 207 times I had 0.0029. 163 times I had 0.2727, which was the actual observed value. Yes?
So if I understand correctly, then it doesn't matter whether you just permute the rows or just permute the columns or permute both, you're going to get the same results?
Well, no, the p-value is not going to be exactly the same.
Okay.
Yeah, it's depending on the C number or something like that. But yeah, you're going to get just about the same results.
Okay.
So it doesn't matter. Let's actually take a look at what a particular resample will look like. So I just used the boot.array function in much the same ways we've done before to look at the code on your own. Here's what the actual data looks like, and let's compare this to, I guess actually we already had it written there. No, let's actually compare this to the actual observed data. Let me do a split screen. Okay, so you can see in the cells of the table that indeed that they are different, but take a look at the marginal totals. So N1 plus star, which will be the sum of these two numbers here, is 285. It's exactly the same as what was observed. We can look at some more plots. Here's my own version of a histogram. Again, as we've seen before with the Bootstrap test, I like to actually draw in where the observed test statistic was. That helps visualize what the p-value is going to be. You can see the p-value is like large. There's an EDF plot. You can see with that EDF plot, the chi-square 1 typically does a good job. And we could do my own version of a QQ plot as well. And again, similar results. So, and we've kind of discussed this before, what one could do is, let's say in a research setting, let's say maybe you developed a new testing procedure, and you want to, maybe for a fixed sample size, want to see, well, is this distribution approximation actually working for your statistic that you're proposing? Well, you could do like a permutation test like this to help kind of justify what you're doing. If you have it matched up similar to what we did here, you might say, yeah, your proposal is reasonable. Question, how could you perform the test with the likelihood ratio test? So that's another way that we could test for influence. What would you do? Would there be much of a change? Just do a different statistic. That's it. So instead of x squared, do negative 2 log lambda. That's it. Now guess what? There's actually even a simpler implementation of this permutation test. In the chi-sq.test function, there is an argument called simulate.p.value. If you say true, say the number of resamples you want. Let's say they use B, but that's like our R. And you get a permutation test. Now, note that they don't actually use the same methods that we are doing to get this p-value. In the 1990s, mainly, there was a lot of research done on maybe how to efficiently do these calculations without, let's say, taking a large number of resamples. And there's in chapter 9 of our book talks about some of that as well. And so they're actually using a different method to do this, but it should give you just about the same p-value as well. Okay, let's look at another example. This is, if you remember, when we were looking at the Bootstrap, we looked at the bird data and we looked at a different example of testing for independence 2 where the Bootstrap did not work. If you remember, we had this 3 by 9. We had this 3 by 9 contingency table structure. We have tons of zeros. And our problem was that we were often having rows and columns that did not have any observations in it, which then caused our x-squared statistic to be calculated on a smaller contingency table and thus have potentially a different asymptotic distribution, which really would worry us. Do you think that same kind of problem will occur here with permutation tests? No, because again, you're always going to have the same marginal counts every single resample. So this is a case where the permutation test is actually better to use than the Bootstrap. So let's see what happens. Regular old chi-squared test. X squared is 22.28. Degrees of freedom is 16. P-value is 0.1342. Again, we might be worried if a chi-square 16 approximation actually does work. Let's see what happens with the permutation test. So my code, basically the same. So I'm not going to go through all before. We're just going to focus on the actual calculation results. Here's my new p-value, 0.002. It's quite different. Quite different. Well, why is this occurring? Well, let's take a look at a histogram and also an EDF plot. The red is a chi-square 16. An asymptotic chi-square 16 distribution approximation just does not work. So I guess it's an obvious example then that even though you're maybe often taught, use this chi-square approximation. Remember, x squared itself does not have a chi-square distribution. It's only for a very, very large sample does it have a good approximation to a, well, not necessarily a very good, not necessarily a very large sample, but at least a moderately sized sample it takes for this approximation to work well. We can see here, it doesn't work. So if I had a choice between using the permutation test results or the chi-square 16 result, I would definitely use the permutation test results. In fact, if you wanted to, you could do even a little simulation study to show that indeed the permutation test is holding the correct size in this test. The chi-square approximation is not. Okay, any questions? Okay, so section 4.4 was this non-parametric bootstrap test. We've already done most of it. Let's go to page 455. Now, one of the problems with a bootstrap test, and even with a permutation test, is figuring out how to do the resampling. It's not the same for every single problem. Often it takes some time to think about in terms of what does it mean for the null hypothesis to be true. How can I get it to be true so I can take resamples from f hat 0? And it's not necessarily a simple problem always. And so what the authors present here is another approach that supposedly should work for any problem. Simply, they suggest to do the following. So, f hat itself basically assigns a probability of 1 over n to y1, a probability of 1 over n to y2, and so on down to yn when we're sampling with replacement. What this subsection talks about is how we could modify this 1 over n to be maybe something else. Let's call it P1. This 1 over n to be something else, call it P2, down to Pn, so that the null hypothesis is true. So instead of 1 over n, maybe it's 1 over n minus 2, for example. Some other probability. What ends up happening is this. A connection is drawn with the multinomial distribution. Remember how I said resampling is like working with a multinomial distribution? Well, here are my category probabilities. And you can construct a function or statistic such that the null hypothesis, or construct it so that it's in terms of these probabilities here, so that the null hypothesis is actually true, that theta, let's say, is equal to something. That's the big picture. This draws also on something that, if you've taken some PhD advanced inference courses, draws on the Kullback-Leibler information number. Does that sound familiar by chance? It draws on that. The Kullback-Leibler is actually connected to the AIC, or actually the AIC statistics connected to that, I should say. And it uses that to, let's say, look at deviations between different distributions. One under, not necessarily the null hypothesis, one under the null hypothesis. Okay. Oops. So that's the big picture of what's happening here. We're actually going to skip the section. Of the 4 times I have taught this course, I've only been able to do this section once we had time. But I skipped this section because I know in actual practice, I've tried to do this before, I've had some difficulty actually implementing this because it actually ends up being a very tough minimization problem or optimization problem. You can see on page 456, I'm working with some a Lagrange expression, if you're familiar with what those are. And I've had some difficulty with it. The book does provide a particular function, exp.tilt. This procedure here is often referred to as exponential tilting. I haven't really seen it used too much. I mean, I think it's a very cool idea, but like I said, I've had problems implementing on my own from some research problems. So we're going to skip over it. You're welcome to read it, though. We'll get to page 471. A studentized bootstrap method. So, what we talked about in the past, it's nice to have a pivotal quantity if you can get one. Of course, in a non-parametric setting, nothing's really going to be exactly pivotal because you don't have some distributions that you're working with. So what sometimes we do in a non-parametric setting then is to work with a studentized statistic. It kind of mimics the idea of a t-statistic. And hopefully you hope that it's going to be, let's say, closer to being pivotal than if you didn't use it. And so you could then work with a studentized statistic in this particular setting, in a hypothesis test setting. So let's say our hypotheses are this: theta is equal to theta 0 versus theta does not equal theta 0. And so here's our studentized statistic. T minus theta 0 divided by the square root of V0. I'm going to call this Z0. That V0 means a variance is calculated assuming the null hypothesis is true. This is often it can be difficult to figure out what that is. So what's often done instead is this V0 is replaced with just, let's say, V, just some variance estimate that's not necessarily constrained. The reason being is because if the null hypothesis is true, of course, V is going to be close to V0. Now, to do resampling here, what I can do is for every single resample, and I might as well put an R here just to emphasize that this is for every single resample, calculate T star, subtract off theta 0 divided by square root of V star 0. We'll call that Z0 star. So, we've done a similar thing here to what we first saw back in Chapter 2, where we're basically working with the idea of a statistical function. If I have T of F, then I can work with T of F hat, for example, and T of F hat star. So you might be wondering here, well, notice here I have theta 0 here. Why isn't this T? Well, if you're sampling under the null hypothesis, and you're calculating that statistic under the null hypothesis, of course, T will be theta 0. Be careful with book's notation when you read it. I don't think it's the best. I just have some comments there about that. And so now you could calculate p-values in basically the same ways that we've done before, but now instead you're working with a studentized statistic. Okay? No big deal. Now, our book spends most of this little subsection talking about a different method to do hypothesis testing using Bootstrap. So again, let's say that here's our hypotheses. Here's my test statistic. In the book, they don't put V0 there. Probably, if possible, it would be better to have V0 there, but in the book, they just put V there. So there's our Z0. For every resample, then, they say to do this. Calculate T star, subtract off T, divided by V star. We'll call this Z star. Now compare this to what we had just done on page 71. Notice you do not see a 0 here, a 0 there. You do not see a theta there. The reason being is because we are actually not taking the resamples with respect to HO anymore. We're taking it with respect to just F hat itself. Boy, that simplifies things for us, doesn't it? Well, the problem is it gets away from the idea of what we do with hypothesis tests. We assume the null hypothesis is true, and our distribution from which the data comes from is under the null hypothesis. They talk about this approach. And how do you calculate your p-value then? The probability that Z star, absolute value of Z star, it's a two-tailed test, using the idea that we had with the permutation test. probability absolute value of z star is greater than the absolute value of z0 given f hat. Or you can calculate it using this method as well. Now, this idea of doing hypothesis testing was advocated by Peter Hall and I think her first name is Susan Wilson in 1991 in a biometrics paper, where you don't have to resample under the null hypothesis. In 1992, Tim Shirani of Efron and Tim Shirani fame, they're the ones who came up with the first Bootstrap book in 94, I think, actually did a reader reaction paper. And we had an argument going on in the statistical literature about, is this really the right approach or not? And Tim Shirani says, no, you can't do it that way. You have to resample under the null hypothesis. Sure, there are some simple problems where you will get the same answer, as what was actually illustrated by Hall and Wilson for their simple problem they were working at. But generally speaking, you should always resample under the null hypothesis. Hall and Wilson actually then did a reply to this, and they said, no, you're just not looking at things right. Well, I agree with Tim Shirani that you need to resample under the null hypothesis. In one place where I saw this from my experience that this was needed was when I was actually doing my dissertation, I developed a method where I didn't have to resample under null hypothesis. I used the studentized statistic approach. I looked at the size of the test. The size was correct. But where the problem comes in, and this is what Tim Shirani says, where the problem comes in, you can have extremely poor power. So I agree with Tim Shirani. If outside of this class you would do what Hall and Wilson do because it's easier, just don't tell me about it. But I agree with Tim Shirani. And you can see that the book authors don't focus on this alternative approach much. Okay. There's just a few other things in this chapter you're welcome to look at if you want to, but you're not responsible for. In particular, there's an interesting section on multiple testing in terms of, let's say that you want to do multiple comparisons of means and stuff. This section talks about how to do that with respect to the Bootstrap. I do want to point out that there is a nice way to do this in SAS, actually, called that's under the procedure proc-mult tests. This is one of the few SAS procedures that I know of. Well, I have to admit I haven't used SAS for 3 or 4 years at least. So maybe there's something newer there. But this is a nice procedure because it allows you to resample vectors of data rather than just maybe necessarily individual values. So imagine, for example, with the project where essentially we're resampling vectors of data. Well, I coded all that stuff originally in SAS. So I was using SAS using proc-mult tests. In fact, all my dissertation was a lot of proc-mult tests. Not using proc-mult tests for the purpose of multiple testing, but using it just as a way to get my resamples. I just want to briefly mention about the project. You don't need to get out, it's just going to be real brief. You should be able to now do the entire project. The one thing that we had left before today's class was this part D, do a permutation test. So, based upon what we saw for a hypothesis test for independence with the bird data, you should have a very good idea of how to do the permutation test now with respect to testing for SPMR. Okay. Are there any questions? Yeah.
For the E part, the first go on the next page.
Excuse me?
The next page. In the first one, perform the bootstrap of SPLA, only for the bootstrap or for the 3 methods.
Use all 3 methods. I purposely put that there to make sure that at least for the first so that I know exactly what you get for the first data set. And I focus on that for grading, because that tells me then if you're going to get part 3 and part 4 correct or not. If you don't get part 2 correct, then I know I'm going to have to probably look more into your code on part 3 and 4 to assign partial credit. That's why that's true. Sorry, it wasn't specified that I wanted you to do all the tests. Any other questions? Okay, let's get into Chapter 5. So Chapter 5 talks about now confidence intervals. We obviously have already talked about confidence intervals before, the basic interval and the studentized interval. We'll review those, but we won't necessarily focus on those. But what we will primarily do in this particular section is introduce two new confidence interval methods, one called the percentile interval and one called the BCA. The two best confidence intervals for the Bootstrap, generally speaking, are Studentized and the BCA. Those are the two best. The BCA was introduced by Efron in a paper in the late 1980s. But we will review again some. So section 5.2, this kind of put into the big picture of what we try to do with confidence intervals, and then get to the idea of the Bootstrap. So again, let's say that we're interested in coming up with a confidence interval for a parameter theta, and t is going to estimate theta. Our estimated variance, or var hat of t, is going to be just generically denoted by v. There's a variety of ways that we've learned so far to estimate this, estimate the true variance. Quantiles at t minus theta. This might be a little bit new notation for us. Are going to be represented by a sub p. So what that means is the probability that t minus theta is less or equal to a sub alpha. Or in other words, if I were to draw this out, so this is the distribution of t minus theta if it was continuous. A sub alpha means the area to the left of a sub alpha is alpha. And so that's like a left quantile as long as alpha is less than 0.05. And a sub 1 minus alpha is a right side quantile. Then what we could do is say then that the probability that t minus theta is between these two quantiles is 1 minus 2 times alpha. We can do some algebra so that we get to this part right here. So that theta is just in the middle, and essentially what we have here is a confidence interval. We think in terms of observed quantities, a confidence interval for theta. This is the book's notation. The lower limit of the confidence interval is going to be theta hat sub alpha, just notation. Observed value of t minus, notice how this is the upper quantile, that right quantile. The upper limit is theta hat sub 1 minus alpha, t minus, then this lower or left side quantile. The problem, of course, is for actual calculation is, well, what are these quantiles? We've talked about this some. How can you get these quantiles? You know, one of the things that you could do is rely on asymptotics. Maybe you have t being a maximum likelihood estimate for theta, and you can use then the asymptotic normality of t then to come up with what these quantiles would be. So, for example, the t minus theta distribution can be approximated by normal random variable with mean 0 variance v. Then in that case, this is what our interval would look like. We replace, the a with a quantile from a normal. How do we get v? Well, you use the inverse of the observed Fisher information matrix. Observed Fisher information. You could also use asymptotic normality of the MLEs again, but go a little bit further in terms of getting something that will be, let's say, more robust. You can use a bias correction, and you can maybe use a variance estimate from the Bootstrap. So for example, this is what our interval would look like in this particular setting, where t minus b, where b is this bias correction, or the estimate of the bias, I should say, and you replace v with v boot. If we're in a totally parametric setting, you should be able to derive what these actually are. We also learned about then the basic bootstrap confidence interval, which now says, well, let's use the bootstrap now to estimate these two quantiles. So we use quantiles from the distribution of t star minus t. You could derive those, or you could actually use actual resamples to estimate them. And again, we have a way to simplify it. Of course, this minus t here, we can combine it with a t there, and we get a 2t. Okay. We could also do a studentized bootstrap confidence interval as well, where essentially what we're doing is replacing the standard normal approximation that we had with the very first interval. We're replacing it with using the bootstrap to estimate the distribution of z star. And so you can get the corresponding then quantiles to replace those quantiles from the distribution of the standard normal, and there's your interval. Okay. So, generally it shouldn't be new, but it's nice to put this all into one context of all these different kinds of intervals that we can look at. Now, also we've said that, well, these intervals work best when the variance of t is not a function of the parameter that's actually being estimated. And we said, well, maybe we can come up with some kind of transformation of our statistics so that then the corresponding variance no longer depends upon the parameter. So how about we have some kind of monotone increasing transformation. We call it h of theta. If you want to do something simpler, just call it eta. This is the book's notation. Then our transformation of t itself, h of t, how about we call it u? So then using the delta method, we can come up with the variance of u, in other words, the variance of h of t, which of course would be just the first derivative of h of theta, evaluated at t, squared times your previous v. Now that's our new variance. We can call it v sub u, variance of u. Then my confidence interval for h of theta then is h of t plus or minus value from a standard normal times the square root of v sub u. Of course, though, we want a confidence interval for theta itself. So what can we do? Well, we have this nice monotone increasing transformation. So what we could do is use then the inverse function with h to find this in terms of the theta scale, we can say. Remember, we did something like this when we were looking at the arc sine transformation for a confidence interval for a population proportion. You could do this same idea by using the asymptotic normality of MLEs. So h of t is asymptotically normal. Do a bias correction now with it, and also use a variance estimate from the bootstrap. We could do the basic bootstrap confidence interval as well. Now for every resample, calculate h of t star. So notice how we have h of t star here. So just essentially it's just the basic bootstrap confidence interval, but you have h of t and h of t star in there. And again, we'll work with then the inverse transformation. And lastly, we can work with the studentized bootstrap confidence interval as well, where now we have h of t, h of theta, h, first derivative of h of theta evaluated at t, absolute value of it, times the square root of v. Just make sure you see where that denominator comes from. It comes from basically taking the square root. Okay. So then for our resample quantities then, we have a Z star, we have H and T star, we have V star as well. And again, to put this in the context of the correct scale, we can use then the inverse transformation once again. Okay. If we want to go totally non-parametric, you could always replace those V's with non-parametric delta method estimate, VJAC, VREG, VBoot, and do everything totally non-parametrically. It's resample from the EDF and so on. Okay, so that takes us to an example. It might be a good place to stop, though. So why don't we just do that? Are there any questions? Okay, that's it for today.